Chapter 1, Module 3. In this module, we shall deal with sets with ordering defined on it. So, let us start with defining order on a set and discuss various different types of orders like partial order, total order, etc. A binary relation rho on a non-empty set A is called a pre-order if it is reflexive and transitive. That is, for all A belonging to the set A is related to A, and for any ABC belonging to A with A related to B and B related to C implies A related to C. We denote a pre-order by A less B whenever A is related to B and say that A precedes B or B follows A. Let us consider an example that we consider the set R of real numbers, define the relation that x less y if and only if x is less than equal to y. This less than equal to means the usual ordering of real numbers. It can be seen very easily that this particular relation x less y is a pre-order. Similarly, if we take the set as R2, then any two points in R2 like x1 y1 and x2 y2, they are related by a pre-order less if and only if x1 square plus y1 square less than equal to x2 square plus y2 square. It can be shown that this relation less is both reflexive and transitive, so that it becomes a pre-order. Consider another example, that we take a set X and consider its power set Px, define a relation that A is related to B if and only if A is a subset of B, then it is once again a pre-order. If we observe that in example 1 and 3, one very interesting thing happens, that x less y and y less x both imply that x is equal to y. But in the second example, this is not the case. It can be seen if we choose the points 1 0 and 0 1 from R2, then of course 1 square plus 0 square is less than equal to 0 square plus 1 square, and similarly 0 square plus 1 square less than equal to 1 square plus 0 square, but still the points 1 0 and 0 1 are two distinct points in R2. With this observation, we define partial order on a set. A pre-order is said to be a partial order if it has an additional condition of antisymmetry. The condition antisymmetry says that whenever two points A and B are taken from A is related to B and B is related to A will imply that A is equal to B. And in such case, the set A together with that relation partial order is called a partially ordered set or a PO set. Of course, as we have already pointed out, example 1 and 3 are examples of partial ordering, but example 2 is not. If we again put a condition on a partially ordered set as follows, that whenever 2 points A and B are taken from A, either A is less B or B is less A, then this particular partially ordered set is called a totally ordered set, and in such case we call that set A a chain. We once again observe that example 1 is actually an example of a totally ordered set, while example 3 may not be a totally ordered set. One more important type of partial order is defined here. A partially ordered set A is called a well ordered if for each non-empty subset B of A, there exists some B0 taken from capital B such that B0 is less B for all B belonging to the set B. Such an element B0 is called a first element or least element of B. We observe that the first element of a well ordered set must be unique. Suppose a well ordered set A has two first elements, say A0 and B0, then A0 being the first element, A0 is less B0, and B0 being a first element, B0 is less A0. Now, since A is a poset, by antisymmetry we have A0 is equal to B0. Secondly, if we start with a preordered set A with the preorder less, and if we take a subset B of A, then B always induces a preorder from the order of A. Further, B is a partial ordered set if less is a partial order defined on A. B is a totally ordered set if the order on A is a totally ordered. B is a well ordered set if the order on A is a well order. So, without loss of generality, we may denote the order relation on B by the same symbol as used in case of A. Consider the following examples. If we take the empty set, then it is always well ordered. If we take any singleton set, it is also well ordered. The set of all positive integers is well ordered with the first element 1. In fact, the set of all negative integers is also well ordered with the first element 0. Now, the following theorem gives a partial estimate for the class of well ordered set. It says that every well ordered set is totally ordered. Suppose we start with a well ordered set A with a relation less. Choose any 2 points A and B from the set A. Then of course, the set consisting of only 2 points A and B is a subset of A, and by well ordering there must be a first element for the set AB. That means either A or B is the first element of this particular set. If A is the first element, then A will be less than B, otherwise B will be less than A. Hence, either A less B holds or B less A holds. Arbitrariness of A and B proves that the well ordered set A is totally ordered. If we state it contrapositively, then we get the corollary that if a set is not totally ordered, then it is not well ordered. In view of this corollary, for any set X with at least 2 points, A less B if and only if A subset B, this defines a partial order on the power set of X, that is not a well order. In what follows, we are going to introduce two basic principles of set theory. The first one is Zorn's lemma and the second one is Maximality Principle given by Hausdorff. We shall show that these two apparently different principles are actually equivalent. In what follows, we use the following convention. When we write the sign less than equal to, we mean that it is a partial order defined on the set. And if we write A less B, then we mean that A is less than equal to B and A is not equal to B. Now, Zorn's lemma appears in proofs of various non-constructive existence theorems throughout mathematics. We have seen lot of examples, lot of application of Zorn's lemma. The statement of Zorn's lemma is as follows, that let X be a partially ordered set with the partial order less than equal to. If every totally ordered subset of X has an upper bound, then X contains a maximal element. Now, we need to clarify the meanings of the terms upper bound and maximal element. An upper bound of a chain or a totally ordered set A of a partially ordered set capital X is an element u of X such that A is less than equal to u for all A belonging to capital A. By a maximal element, we mean an element M belonging to a partial ordered set capital X such that whenever M is less than equal to S, then S should be equal to M. A chain A in X has an upper bound. That does not mean that the upper bound will be inside A. It could be inside capital X, but not in A. M is a maximal element of X, once again does not mean that M should be bigger than all the points of capital X. What we mean by that is, it is not the case that X is less than equal to M for all X belonging to capital X, because any two elements in capital X need not be related. We are in a poset. A partially ordered set may have more than one maximal elements. Consider an example that we start with a set of real numbers R with natural ordering. Then the set of negative real numbers has an upper bound 0 in R. That means we are getting a number 0 which serves as an upper bound of the set of negative real numbers, but that particular element 0 is not included in the set of negative real numbers. Also, no negative real number can be an upper bound. If we take the set of all integers z, then z has no upper bound in R. In this example, we consider the set capital X of all integers strictly greater than 1. That is, we take the set X as a set consisting of the numbers 2, 3, 4, etc. Define an order on capital X by A less than equal to B if and only if B divides A. It can be checked easily that it is a partially ordered set. Each prime integer is a maximal element of this set. Hence, there are infinitely many maximal elements of the set capital X. Now, we observe a few things, that Zorn's lemma does not provide any method to find a maximal element. It only guarantees its existence. Zorn's lemma does not give any estimate for how many such maximal element can exist. One could have stated Zorn's lemma dually in terms of minimal element as well. Now, let us talk about Maximality Principle, which was given by Hausdorff in 1914. It says that if we start with a partially ordered set X, then every chain in X is embedded in a maximal chain. That is, if A is a totally ordered subset of X, then A is contained in B, where B is a maximal totally ordered set in capital X. We shall now establish that the two principles which we had pointed out here, the Hausdorff maximality principle and Zorn's lemma, these two are equivalent. If we state the theorem formally, then in a partially ordered set X, the following statements are equivalent. Number 1, the Hausdorff maximality principle. Number 2 is Zorn's lemma, and number 3 is that if every chain in X has a least upper bound in X, then X has a maximal element. Now, let us prove this result. We want to prove 1 implies 2. Suppose every chain in X has an upper bound in X. Then condition 1 says that there is a maximal chain M in X. By hypothesis, there is an upper bound, say small x, of capital M in capital X. Since X is an upper bound of capital M less than equal to X holds for all M belonging to capital M, and therefore, M union the singleton X is a chain in capital X. By maximality of capital M, we then have capital M is equal to M union singleton X. But that means the point X should be inside capital M. Consequently, this element X is a maximal element of capital X. Let us prove 2 implies 3. This implication is obvious as 3 is a stronger statement than 2. Now, we prove the final one, that is 3 implies 1. Let Q be the set of all chains of capital X partially ordered by set inclusion. If the collection C alpha belonging to lambda is a chain in Q, union C alpha alpha belonging to lambda is a chain in capital X, which is a least upper bound of the collection C alpha. Thus, Q satisfies the hypothesis of 3. Hence, it contains a maximal element, call that maximal element capital C. This C is a chain in capital X. It is easy to see that C is a maximal chain as we are looking for. Next is another very well known principle. It was given by Zermelo and we call it Zermelo's theorem. It says that every set can be well ordered. It is to be noted that Zermelo's theorem assures the well ordering, but not provide any specific method of construction of well ordering a given uncountable set. Secondly, the well ordering guaranteed by Zermelo's theorem is not necessarily unique. Now, if we consider the real numbers, we already know that it has a usual natural ordering. It is clear that the well order assured by Zermelo's theorem cannot coincide with the usual order of real numbers. We point out the main advantage of well ordering theorem now, that it says, rather it enables us to extend the principle of mathematical induction for positive integers to any well ordered set. Principle of transfinite induction says that if B is a subset of a well ordered set A, such that for every A belonging to capital A, the collection C belonging to A such that C less than A is a subset of B implies A belongs to B, then the set B should be equal to A. We want to prove this theorem. So, we start with a subset B of a well ordered set A. and if possible, suppose A minus B is a non-empty set. If so, then there exists an element which is a least element of A minus B, and that is always the case because A minus B is a subset of A and A is well ordered. Using the definition of least element, we get that the set of all points C taken from A with the condition that C is less than A, that particular set should be contained in B, because A being the least element, any C satisfying the condition C less than A cannot be in the set A minus B. So, this particular subset should be a set properly contained in B, but it says that whenever this thing happens, the point A will be inside B. Therefore, we get a contradiction that the point A is in A minus B as well as in B. So, it is in the intersection of B intersection A minus B, which is not the case. Therefore, A is equal to B. If we agree to accept that every set is well ordered, then we can apply the principle of transfinite induction to prove various results. Now, the question is, are we assuming something more than axiom of choice? We shall see in the next chapter that all these results, Zorn's lemma, Zermelo's theorem, Hausdorff maximality principle, all are equivalent to axiom of choice. With this, we end chapter 1.